Let's just kind of get started then. All right, well, welcome back to the third session of Edgar's Guide to Python and Neuroanalysis. And today, despite the fact the course title is about Python and neuroanalysis, we can actually visit the topic of how you can manage code, how you're going to organize code, namely in the form of Git and GitHub. So that's going to be the first chunk, and then towards the latter half of the session today, we're going to cover and dive into what I said in the syllabus, the NumPy, which is a numerical analysis package in Python. But I did really want to cover this because as soon as you start really doing more and more coding, like you actually put together code that's not like, more complex than just mere 4 or 5 lines of code. And if you start having multiple files of these things, then organizing them and keeping track of the changes you made becomes imperative. Like it soon becomes to the point that you really wish you had something like that to begin with, or otherwise you'd be in a huge mess and you'd be wondering which is the last code you actually ran, or what's the code you actually used in the last figure you published, and now someone wants to see if they can replicate it and you have no idea what to do. Okay, so as I've already started, keeping track of your code is getting more and more critical. As you work on more complicated code, this is really important, not just for the sake of yourself, but also sake of working with other people. If 2 or more people start working on the same piece of code, which could happen, and is actually highly encouraged to kind of get to that point at some point, you actually want to know what are the changes other person made. Now, so a couple common approaches people take have been like keeping a copy approach. So it might look something like, well, you just keep a copy of a file. Before you make a change, you copy it so you have a one version of it laying on your desktop, or hopefully maybe somewhere a bit organized in folders, depending on how tidy you are about organization. But this actually can get out of control very, very quickly. So, for example, this could be a real scenario. So you have something like analysis. These are MATLAB files just for a record of it. You see you have analysis, you have code for poster 2015, you have complete analysis, but you obviously have complete analysis real final. You also have full analysis, but there's also final analysis. But there's a final analysis with a quick fix. And there's a quick analysis with the fixed up. So guess which is the latest? It turns out it's a quick analysis fixed, right? I mean, it could be basically. That's the point, is that, and date is not always the most indicative, because maybe you make a copy and that's the latest version of the copy and you made some tweaks and quickly decided, okay, that's not what you wanted. But you say, oh, I named it differently, so I'm just going to keep it. The problem with these approaches usually are that you make a copy and you're quite confident you know what's the latest because it's fresh in your mind. Just wait 3 months and you have no idea what you've done. Okay, so a better approach would be something like this, perhaps, like where you now have a copy made, say like now a project level copy, and they're completely dated. Great, right? Now at least you know what's the latest. The issue with this is now, do you know what has changed? What's the difference between my 2013 October 3rd versus the latest? What have I changed, right? If I now use the latest code and I run into a bug, how do I know what was the change that caused my bug right now? And I mean, this is not just for coding, right? So the point being here is that you actually can see stuff being applied to something like paper. So when you actually work on manuscript, your PIs and collaborators, this is actually unfortunately a real scenario in which we basically have, this is all different revisions of a one manuscript. So you can see we try sort of a versioning, right? We attach some numbers at the end, and every time we change, we put the initials of whoever changed it. It kind of gets out of hand very quickly. So you kind of wish there's a better system by which you can track different versions without having to create hundreds of files corresponding to what is otherwise the same manuscript or same piece of code, and have an easy way to tell what has exactly changed. So that's why I'm introducing you to Git. So hopefully you've had all chance to install Git as you were supposed to. I know I haven't quite given you a command to verify you've installed Git and everything is working, but if you ran through the whole installation and as long as the installation didn't seem to have panicked, you're probably good to go. We'll see it very shortly. Okay, so you're probably wondering, okay, what is Git? What is this piece of software Edgar made me install on my machine? Well, so Git has a formal definition, and it's a distributed version control system. So I could just leave it like that and assume you'll understand what this means, which is probably not the case. A more practical definition is that it's a piece of software that lets you keep track of changes you make to a piece of code, or in fact any text files, or any files for that regard, and with an ability to actually revert back the changes. So, okay, who should use Git? Now, if you're taking the course, and given the fact I'm teaching this as part of what's otherwise called a Python course, obviously, if you're a Python programmer, I'm suggesting you ought to be using Git. Or if you're a programmer of any sort, you probably should be using Git. But here are some rundowns of who probably should be using Git. So if you ever made a change to a file that you wish you could undo, if this is something you've done in the past, Git is for you. If you just want to try out some new changes without the fear of breaking it completely and not being able to go back, Git is actually very helpful for that. You just want to keep track of different versions of a file. So here what I mean is like maybe you actually tried two different things in your code and you actually just want to keep it side by side. Being able to switch back and forth just to try which one works out better, Git actually lets you do that easily. Also, you want to know what are the changes that were introduced. So a couple months down the line, you were wondering, well, what's the particular change I made like 2 months ago? Because that seems to have changed something about my analysis. Maybe your current analysis result and what was analysis result back then doesn't agree anymore. You want to know exactly what has changed. Git has a way to easily tell you that. Also, this is a perfect way to collaborate with others, as I mentioned. Like if multiple people are working on same piece of code or same collection of code, you actually want to know what are the changes each individual person has made. It makes it easy for people to get caught up and also just be able to make changes without fear of messing with other people. You also, okay, this is another one. This is kind of collaboration within yourself scenario. So if you actually imagine coding on multiple computers, it might be the case that you actually want to use Git to keep track of changes introduced when you're working on one computer versus another computer. Maybe you're working in the lab on the desktop, and then at home you're maybe working from laptop. Git lets you have the two same code shared across and be able to keep track of changes made wherever you are. And if you just have the secret wish of just going back in time, this is as close as it gets to it. Okay, so how to think about Git. Git is your file backup system. Git is your change logging system. And Git is your file code sharing system. So if you remember anything about what Git is good for, these are 3 main points. Okay, so let's now talk about how Git actually works. So the Git works at the level of a folder or directory. If the terminology directory is not familiar to you, this is a good chance to get used to it. It just literally means folder. It just is a cooler way to say it. You sound a bit more computer sciencey this way. So I'm going to keep on using directory because it comes up all the time. But in Git, you turn a directory into what's known as a repository. That's just a Git terminology to indicate now this is organized under Git. It keeps a history of what's called local commits. So commits are basically a collection of changes that you pack together, and you're the one who designate that these changes together consist a commit. So it will look like a history of commits, and each point representing a particular commit. Remember, commit is not just a single change, but it's a collection of changes. So here's a more practical example. Say I have a folder called My Project. It contains a couple files in it. It already contains a README file. It contains some analysis code I've written and maybe some data. Now, I already turned this into a Git repository. So this entire thing is a repository. And I first started out with the very first initial commit. And because I just added these files, my changes are addition of all these 3 things. They are all part of one commit indicated by the green. Okay, and each commit is associated with the message. Here is initialized repository, just to indicate what the commit was about. Okay, all in good, nothing really fancy yet. Now I changed the README. I decided to give a bit more description of what this project is about. I added some descriptions to it. That's the only thing that really changed. So that's part of my new commit. I put the changes. I designate that as my new commit, now shown in blue. But other 2 files haven't really changed. So under this new commit, which is shown in the blue, it really has only changed the file, the README. So that's the one that actually tracks. But given the other files haven't changed, if you were to look at that particular slice of your code, it comes with the unchanged files, analysis.m and data math, as it was from the first commit. So when you look at the code in Git repository, you always look at particular commit. And the commit can change particular change that was introduced at that commit, as well as all the other files from the most recent commit. Okay, now if I make some additional change, now I really make a changes to my analysis. This time only analysis change. I commit this. I call this commit. I put the message to commit to be fix bug in analysis. So under that particular commit, which is indicated by the red circle, now you have the latest of analysis, but you also have the most recent version of the README, which is in blue, and the most recent version of the data.mat, which hasn't really changed since the initial commit, so that's still showing green. So the key with the Git is that it lets you organize in terms of commits, but if things hasn't changed, it doesn't make a duplicate. It just keeps on referring back to the latest things you actually done, so it doesn't waste space all the time. So this is not the same thing as keeping folder level copies, right? It just takes tracks the thing that was changed, and that's the only thing that it literally keeps a copy of, sort of. All right, so again, these are commits. Each commit is associated with what's known as commit hashes. These are signature of the commit. You seldomly use them, but it could be useful to identify exactly which commit you're talking about. And for more human readable form of tracking, you actually put messages. This is to indicate what have you done with that commit. Okay, when you start a Git repository, there are two routes to it. You can either turn an existing folder on your computer into a Git repository, and we'll actually visit this using a command git init. Or if there's already a Git repository that's shared online with someone, well, you can do something called git clone, which takes the online repository and makes a copy locally. And when you do so, it takes the whole Git repository, puts a copy, and then it's already a Git repository on your machine, so you don't have to do git init on it. So for us, what we're going to do now is actually try this out and make a Git repository for the first time by turning an existing folder into a Git repository. So yeah, I'm going to actually visit this point of telling who you are. So Git needs to know who you are because every time you make a commit, it associates it with the committer's information. This is particularly helpful when you start collaborating with others, so that way every time someone makes a new commit, you know who's the one that just made that commit. And with that, you usually associate the name and email address. So we'll go configure this shortly in your Git system. And what we're going to do now is we're going to work on and create a very simple Python project. So make a new folder, turn it into Git repository, and we'll put some file in it, makes a couple commits, and that's how we're going to do right now. Any questions so far? Makes the thing's pretty clear. All right, so with that, what I'm going to try to do is to try to work on both the Windows side and then the Mac side. So I'm going to mostly work from within Mac, but there are important differences. I'm going to show how it looks in Windows. So the very first portion I'm going to show both for the Mac and then immediately get to the Windows. So for Mac users, what you want to do is open up your terminal. So that you can do, hopefully you already have done this, but if you go to Applications, if you now go to Utilities, there's a terminal application, so make sure you open that up. Okay, so that's the starting screen for you guys. For Windows users, let's see how well this thing works. Windows user, if you start, I know this is going to be a bit clamped here. If you look for Anaconda prompt, so this is what you should have already used to verify Jupyter Lab. If you open this, so this is a particular version of command prompt that comes because you've installed Anaconda. It's beneficial because it has all the right setups for using Anaconda, and this is also the screen from which you can do a lot of Git-based commands. All right, so from here on, it's mostly the same, so I'm going to mostly be in the terminal on the Mac. When there are differences in commands, I'll point them out. I've also written them out on the board. So there are only one command that you really, is it the only one command? I think there's only one command that's dramatically different between the two. In Mac, you guys will be using a command called ls to list the content of a folder. On Windows, the corresponding command is dir for directory. And everything else is practically the same. So when I say list, I'll try to also say dir for Windows, but just do the conversion in your head if I fail to mention that. Okay, so in the terminal, so for those of you who are probably not that familiar with what the terminal is, it's nothing but a very simple text-based interface to work with your computer. A couple of decades back, this was the only way to work with computers, and I guess you guys think you're fortunate because you don't have to do this anymore. quite honestly, this is still one of the fastest way to work with a computer. And if you know exactly all the commands you want to run, this could be very, very efficient. So as you start to work and build your experience doing coding, I do strongly recommend that you gain some familiarity with the terminal because it really can improve your efficiency. And as far as installing a lot of tools for programming, a lot could still be based on terminal. So not being afraid of it is very critical. And it's not that bad. So here we're starting out somewhere. What you can, basically this is actually just looking at a particular folder. You're always somewhere in your folder or the folder structure. Here I'm in my what's called home folder. You can look at the content of where you are just by typing ls and hit enter. For Windows guys, that's dir. And list a couple bunch of folders. So here in this my home folder, there seems to be applications folder, desktop folder, documents folder. So you can, for example, now go to documents. You can change directory to CD or just move into a particular folder by CD followed by the name of folder you want to move into. So I hit. Now I'm in the documents folder. Now if I run ls or dir again, I get to see the content of the documents folder. And if you want to see, okay, what does this look like in my GUI, more nicer interface, on Mac, you can say open dot to say open where I'm right now in a Finder. For Windows, you can say start dot. So let me actually do the same thing. I go to Documents. If I say start dot, it opens it up in Explorer. So nothing too difficult so far. All you're doing is just navigating around folders just within Terminal. So what we're going to do now is that now inside a Documents folder, both in Windows or Mac, we're going to create a new folder that's going to contain our Python code. You can create a new folder by make directory or mkdir command followed by the name of the folder. And I'm just going to call that my Python project. You can really call whatever you like. I created it. Now if I just do list or directory again, you should see the newly created folder. And I can now move into that folder. And if you do list again, it should be empty. You just created an empty folder. Okay, let me just repeat it quickly on Windows side. So here I'm just going to say Python project, move into Python project, and that's it. Empty. Okay, so so far so good. Nothing too exciting yet, right? What we're going to do now is take this folder and turn it into a Git repository by one command called git init. So if you're inside a folder and run git init, what it does is take the current folder and turn it into Git repository. So let's just do that. Okay, so it initialized and turned into Git repository. Good, congratulations, you've just successfully created your first Git repository. And obviously nothing is really that exciting about it. There's nothing exciting really happening here. If you now take your Finder Explorer and look at your folder, it still looks just as empty, right? Nothing seems to have really changed. Well, it turns out that there's a way to list what's called hidden files. So inside the folder, if you do list ls with -a, and for the Windows, the command's a bit different. For Windows, there's actually a chance you can just see it. So let me actually do the git init here. And if I look at it, it doesn't see it. Oh, this is where I'm going to hit the limit of my. No, actually, I think you can see it. Okay, sorry, Windows, I totally forgot the command. Okay, you can trust me to say like, oh, yeah, this is the part I will have to edit my video later. So if you were to list the hidden files and hidden folders in either Mac or Windows, you would see this folder called .git. In Mac, by default, if you actually put dot at the very front of a name, it's hidden file or hidden folder. This is like one way to hide a folder. And here, .git is a folder that was created by the git init. And all it does is really indicate that this whole folder is a Git repository. And it puts any information that's necessary to maintain it as a Git repository. So for 99.9% of usage on the Git, you will never go into or touch the content of the Git folder. You just forget about it. It's just something that Git has created and maintains to be able to keep it as a working Git repository. So far so good. Everything's working in your terminal. Okay. So now this is a time where we actually do something exciting. We actually create our Python file inside of it. So hopefully you have had a chance to install a Visual Studio Code on your project or on your machine. If you have a favorite text editor, you can totally go ahead and use it. You don't have to use VS Code. But if you don't really have a favorite text editor, or when I say, oh, if you have a favorite text editor that makes no sense whatsoever to you, you probably want to use Visual Studio Code. So if you open it, and let me just briefly explain why I'm making you do this, right? When you work with files like Python or any actually other programming files, what you want is ability to be able to edit what's called plain text. And what I mean by plain text are basically text editors that doesn't insert a lot of things just to format your text. So this is the reason for which, for example, Microsoft Word is not suitable for purposes like this, because behind the scene, if you put any text using Microsoft Word, it puts a lot of extra junk that indicates the font, the formatting, the styling, all this extra information goes into it. And none of this matters for coding. In fact, if you put it in your text file, then your code is no longer functional. They expect it to be just plain text. So what you want is a text editor that just lets you do text editing in the plain text format. And hopefully also code aware. So they actually can highlight your code to indicate that, okay, this is written correctly, so it's easier to see, and provide additional coding friendly features. So for that purposes, you do want a good coding text editor. And there are multiple choices. I mentioned a couple on the Slack channel. But Visual Studio Code at the moment is probably one of the best out there. It's definitely one of the friendliest and feature-rich. So if you don't have other choices that you already had in mind, this is a very good and recommended one. Okay, so enough said about that. Now what you want to do is go ahead and open, you can say open workspace, or if you just say open folder in your VS Code. And what I want you to do is just navigate through your folder. So you should be onto your documents and then find a folder for your project. In this case, it's Python project. You open it. It still should be empty, right? It's not like VS Code is going to suddenly create anything in it. But at least now you've opened that project folder inside VS Code. And this starts to let you do, create text files or Python files inside. So let's go ahead and create our first Python file in it. So you can either just do file new file, and this command, so far the instructions should be identical for Windows. Let me know if there's any hiccups when it comes to Windows. You can just do new file and create a new file, nothing fancy. So before we do anything, let's save this, which I did Command S or Control S. You could just save and give it a name. And I'm going to call this hello.py. I'm going to save it. So that did two things. One, it renamed the file. But more importantly, by the indicating it's .py, this tells VS Code that, oh, you're editing Python file. So you notice that the icon has changed. Now it says, now it looks like this, I don't know. I guess if you don't know what that is, you don't know what that is, but those are two snakes. That's a Python symbol. And if you look at the very bottom right, there's also, it indicates it's a Python. So this means that VS Code now knows you're trying to edit the Python file. And what's nice about this is if you type in things that are Python command or Python function, it will correctly highlight it in different color to make it easier for you to see. So here, because I don't have other good suggestions, I'm just going to print hello world. I don't know, probably for the 10th time in this course. And I'm pretty happy. This looks pretty good. I'm going to save this. And good, I have a working Python file. So get at least this far, make sure hello.py is added to your project. Verify it's added. And once that's done, let's get back to actually the terminal. Okay? So in the terminal, and let me know if I'm going too fast, okay? If you need one more time, let me know. Look at back in terminal, if you do ls or dir, now you should be able to see the file you just created, the hello.py in the project. So far so good. Now one thing I do want to cover very, very quickly is how to run a Python file just by itself. So far we only talk about running Python code in the context of Jupyter Lab. Right? So there you just type the Python code in the cells, you execute cell, everything works pretty nice. But obviously as you work more complicated stuff, you actually want to package into libraries or modules. So we talked about how you can take all your functions, put it in the file with .py, and import it as a module. So that's actually a very common way to use Python. This is a way to make a library, sort of. Another common way is to write a script, something you actually just run by itself. And you can do that. And when you do that, basically, if you put all the commands in the file, you can just run the content of the file from top to bottom just like that. And the way you do that is put those commands or Python code into .py file, like we did here with hello.py, and we run it with the Python command. So you say Python followed by the name of the script. And this just runs that particular script. If you run it, hopefully everything works and you get hello world. So you see what has just happened is you just went to your code, just ran it from the top to bottom. Here it was only one line, so there's really not much to do. But this is a way by which you can have a simple script that just executes the job. So now you know already two main ways of running Python code. In the form of scripts, like the way we just showed, and obviously in the form of Jupyter Lab or Jupyter Notebook we've been working on last week. In real life, when you work with projects, you tend to go back and forth, actually just combine them together. Jupyter Lab is a perfect environment for interactive coding. You just want to try some new ideas, you're developing a new algorithm, developing new analysis, you get results immediately in front of you. You don't have to go back and type Python and run everything from top to bottom. It's a perfect environment to just be very quick in development. However, once you're at the point where everything seems to be working, you're happy with the implementation, it's usually a very good idea to move them into a module so you can reuse it later. So that's one way to just do it. And even on top of it, have another file, like a Python file, which you're going to form as a script, which can just do auto analysis. Maybe every day after a session, you do a recording session or imaging session, there are a couple analysis you want to perform. What you can do is write a script that just do all those analysis step by step, put it in a Python file, and then with this interface of Python, the name of the script, you can just execute the script. So just be aware of both. For 99% of the case, or 90% of the cases, you probably be working with the Jupyter Notebook, and for most purposes, it could actually just suffice. You don't have to use it this way. But if you ever want to run things in batch, or you actually would just want to give a job that just runs quickly, Python script is a good thing to consider. Okay? Yes?
So the Visual Studio Editor, like you don't run your script in this?
That is correct. That's just for editing.
Okay.
Yeah. All right. Yes?
When you're writing your script, you have to be in the folder that the script is in?
Yes. Well, you could specify the path leading to it, but yeah, most commonly you're just in the folder that leads to the script. Okay, so good so far? Your Python file is working? Okay, we really haven't done much about Git yet. This is about Git, so let's actually get back to Git, right? So what you want to do now is to check the status of your Git repository. You say Git status. And I mean, it's a bit lengthy, but hopefully you see, especially highlighted in red, saying there's untracked file hello.py because you just added it. It's untracked because you never committed this into your repository. Basically, your repository is saying you've added something, a file, that I'm not tracking. I have no idea what to do with it. And you're supposed to indicate to Git whether this is something you're just trying, you don't care to keep as part of history, or is something important enough that you should keep. So I want to go back to point. Now we're going to talk about 3 different places in Git, and it's actually best explained in real life, but just a quick overview. When you work with files and changes you make, there are 3 places it can be. One is called working directory. This is basically if you just make a change to a file, or if you just create a new file, they're not committed. It's in the working directory. Before you get to put it as part of the commit, you have to be able to tell these are going to be part of the next commit. So that's called staging. So there's this one extra step of staging, and you do that by adding the files that you want to be part of the commit with git add, and we'll see that shortly. This lets you basically take multiple steps and take your time to form exactly what's going to be part of your next commit. This lets you add multiple files into a staging area. So that's why you can have one commit that basically takes say 5, 6, whatever number of files you just changed together. And once you're happy with the changes that's part of the stage, you commit it and make an actual commit with the git commit command. Okay, so back in here, there's a hello.py. This is in your working directory, the red stage. I'm going to put it into staging area to indicate it's about to be committed by saying git add hello.py. Okay, now let's check status again. If you say git status after you added it, now it's in green because it's staged. And it says these are changes to be committed. But they're not committed yet. They're just changes to be committed. You've staged this change. Okay, so enough said. I feel like I'm happy. I want to actually commit this and make it part of my official history. You say git commit. And as I said, every commit ought to have a message associated with it. This is to be helpful about what is that you just done about your repository. So you do -m and follow this by a string, which is going to be a message. Okay? So here, and it's very typically the case, the very, very first commit, you usually just say something along the line of initialize repository. Okay, so once you're done, hit enter. And it probably has complained to you. I don't know, in some cases it doesn't complain. It has complained to me at least. It's saying like, hey, you haven't really told me who you are. Right? So this is the one I was saying that you have to tell Git who you are. You have to do it only once on your system. So let's do that. You say git config -- global. And I'm going to say, first of all, my name. So user.name. And in my case, I'm going to put the name, user Edgar Y. Walker. So obviously, the content of the quote ought to change unless you want to be me. Okay, so once you type that, enter. Should work. Now, we also have to tell them the email. So that global suggests that do it once, make it part of my machine so I don't have to do it per project separately. There's also a way to do it per repository level, which I really ever use. I always put a global to make it account level setting. So here's going to be user email. And here, put an email address. I actually do put my actual email address. Feel free to put whatever you like. Okay, so now with depending on what status system, it might be the case that it has already actually committed. So in my case, despite the fact it complained, it actually made the commit. In your case, it may not be the case, so do git status check. And if it still looks like changes to be committed or change stage and not committed, do run your git commit again. But if you just say status and if it says nothing to commit, working tree clean, it means that despite the fact it complained, it actually did let you commit. Okay? So when you make a commit like this, you can actually look at what are the commits you made by saying git log. And this gives you a history of commits. So here you can see that it has a commit, it has a message initialized repository, there's a commit hash, which you could use in the future. And here, because I didn't tell them who I am and what's my email, it guessed based on the system. So you use the name of my account and you use the name, it came up with some random address for my email address. So that's fine. There's a way to go back and change for this very first time. If this is what it looks like on your system, you don't have to worry about it. Yeah.
So mine's filled with like an interface where then it says type in your message there.
Oh, you probably.
Do I just negative that?
Oh, yeah. So in this case, you escape out. Let's just do. Shouldn't have come the case. You should do -m.
Didn't do that.
Yeah. So okay, one word of caution: if you say git commit without the -m, it probably open up an interface. Depending on your setup, it should open up VS Code. Sometimes it opens up what's called Vim, which is a particular kind of text editor. If that's the case, either you have a choice of being a Vim expert, or you can actually learn to get out of it. So let me actually demo this quickly, right? So let me go to my VS Code and quickly make a change. So maybe I'm gonna say like, just to make a bit of meaningful, I'm gonna say this prints a message, very useful comment. And I go back, and now I'm gonna go check. Okay, now I made changes. And you guys, others can also follow along. Basically, I just went to my file, made additional change. If you now go get status, it notices the fact you modified it. So again, I'm happy with the change, or at least, so I can just, yeah?
Sorry, how do you get out of
Yeah, I'll show you shortly. So if I just add this file, if I now say commit, it opens this thing up, right? So for those of you who are stuck in Vim, there's one command you probably should learn because there will be future cases where you get stuck in Vim. Don't have to be a Vim expert, just learn this command. Hit escape a couple of times just to make sure you're not in the what's called edit mode. And then you do colon, yeah, Q, enter to get out of it. If that doesn't work, do :q with exclamation mark to really get out of it. Okay? So I'll put that somewhere on my course notes because this actually happens not just in the context of Git, but happens in the context of working in terminal in general. And if you don't have it set up, you could accidentally find yourself in Vim. And if you don't know Vim, it feels like you just completely stuck in it. Just hit escape a couple times and then control Q, colon Q exclamation mark, and that does the trick 99% of the time to get you out of the Vim. It happens when you actually try to make a commit without a message. Right? Basically, if you just get commit, it's like, okay, I noticed that you want to commit, but you haven't given me a message, so I'm going to forcibly open a text editor so you can tell me and give me a message. Okay, so if you want to avoid that, we're just going to be very careful. Just make sure you always put -m and put a message here. So here I'm going to say something like add comment. Okay. So for those of you who, I kind of did as part of like showing how to get out, but for those of you who haven't, go ahead and make some change to your file. It's always good to just practice this a couple of times. Go to the file, make whatever changes you like. Hopefully not a breaking change, but just make whatever change you like. And then go back to terminal. And once you make some change, I can also make some additional change. Maybe I'm going to print another statement. Something like that. Go back to the terminal. Again, check it with git status to see what are the things you changed, or at least the files you changed. And now you can actually say, okay, hello.py has changed. I'm happy with it. I'm going to add hello.py for staging again. Check the status. Now it's green, so I can commit this. I'm going to commit, and I'm going to say print another line. I'm going to commit. And do make 1 or 2 more commits. And once you've done so, take a look at git log again. And this time you should see the history of commits you've made. Okay, so far so good? Yes?
Mine has never been green.
Okay. Did you add that? So when it shows up in red first?
Yeah,
And did you add that file?
I think so. Just add hello.py.
Yeah. And what is it? And when you say git status, what does it say?
It says on branch master, nothing to commit, working tree clean.
Okay. Try making one, change the hello.py again. Maybe you can take a look at it. And let me come around. So make change to hello.py so at least when you say git status, it should say like changes uncommitted. And I'll come and check. Yeah. Okay, let me actually just check. So yeah.
Hit git log,
Yeah.
it comes out YALAB, which is not me, but is my lab. And probably I've been using
interesting.
GitHub in the past.
Oh, okay.
And so, but I don't know what's going on.
Yeah, did you do the git config thing?
Yeah, I did it with you now.
It's interesting.
Yeah, I was setting up.
Yeah. Well, okay. Well, that's because probably you did the first commit before.
Yeah.
So that's fine. Like basically, that commit has already been committed before you did the config. If you now make some change and do a new commit, and if you look at the log, then a new commit should be with your what you just set up. So try that. Okay.
Thanks.
No problem. And all right, quick. Let me try. Is it any luck? Yeah. Okay, that looks good. And now you just want to say git add.
Just git add.
Git add and the name of the file. Yeah. And now if you do git status. Okay. Now you can commit with the message. Yeah. Okay, so hopefully this routine somewhat works. We basically throughout the rest of the course we get to do this all the time, or you're supposed to do this all the time. And I'll remind you once in a while, hey, have you committed your changes? Just so you know you have some history to look back to. Okay, so quickly, a couple more things I do want to cover. I knew this was going to be a Git-heavy session today, so we'll try to see how much we get through. I'm going to finish Git today for sure, and with the remaining time, we're going to jump into NumPy. And if you don't get much of it, we'll do the next session to do full-fledged NumPy and a bit of plotting. So one reason I suggested VS Code is because it actually has a very nice integration with Git. And I kind of forcibly made you go through terminal because I do still believe in knowing these commands. At least it makes you more fluent in Git. But in VS Code, you know this branching looking thing. If you click on it, this is actually a way by which you can control your Git things. So let me show what I mean by that. So hopefully you've committed everything, so there's really nothing showing up here. But say let me make a change. Say like I'm going to print yet another one, say more message, whatever, right? And let me also make a change in what's already existing. So maybe instead of I'm Edgar, I'm an instructor or something like that. Okay, I save it. You see that as soon as I save it, that file that just changed should show up in the changes here. Basically what this is your Git interface. VS Code actually lets you interact with Git and let you actually skip having to do all of these in terminal. Okay, so if I make changes, it came out with changes. If I click on it, it actually nicely shows all the changes I made. There's actually a way to do this on terminal. You actually can do, so if I can go back to the terminal. Again, if I do git status, it should show the fact I changed hello.py. If I actually now git diff, it shows up the changes I made. Right? The red to indicate these were deleted, green to indicate these were added. So it works, it's functional, but I must admit that this looks nicer. Right? VS Code gives you a nicer interface to look at the changes you've made. So if anything, VS Code could be useful just to look at the diff. Because if you're doing diff on terminal may not be as intuitive or as straightforward. Does that make sense? Yeah?
How do you get the changes on the
Let me see. So if that's not showing, is it command palette? No, that's not command palette. Let's see. Is it open view? So if anything, if you do view and then if you do SCM, then that should show it. So try that. Yeah. So SCM stands for Source Control Management, which is a fancy word for stuff like Git. Okay. And as far as you're concerned, the only source control management that exists and you care for is Git. If you're really curious, I can give you 10 other source control management that people have used in the past and no one really uses anymore. Okay, so this is just one way to do it. And let me just do one whole routine of adding, so staging and committing all within here. Okay, so you see plus. If you plus it, that stages it. That's the same thing as doing git at hello.py. Okay? And you're all happy. These are all the stage changes. I'm pretty happy with it. You commit by going to the check mark here. And before you click the check, though, you put your message here. So I'm going to say something like change messages. Now, one comment about your message. I don't know if you noticed, but I've been using what's known as imperative voice. Basically, instead of saying like I changed this, my commits say change command, change the line, add this, delete this, not like added this, did change this. This is because in the future you want to think of what is the commit going to do. Because you want to be able to work in terms of commit. In the future, like when you look at a commit, you want to think in terms of what happens if I go to that commit? What are the changes that this is going to introduce? So convention has been to use imperative voice. So instead of saying add it, I did this, I've done this, you say add this, change this, make this. Okay, so I'm going to just describe what this commit is about to do. It's just a convention, but it's a good convention to follow. Okay, so anyway, I'm going to say change messages, and I'm happy with it. I'm going to commit it. That's it. I committed it. So yeah, I have a feeling now that most of you are probably just going to stick with this, but just know the commands. At least know the fact that there is this idea of add, commit, stuff like that, because they are important. These are corresponding ideas. And the reason I want you to learn those, at least at the get-go, is because this way, if you take it to anywhere else, you can at least use the get command on terminals. And if you have any other GUIs, just not VS Code, but there are many other GUI that comes with Git integration, those terminologies stay the same. You know what they're talking about. Okay, so this way you don't go around saying like, oh, do the plus button thing on VS Code trying to describe add. Okay. All right. So far so good. Makes sense. Yeah, everything's working. All right, so good. So let's go back to the presentation then. All right, well, so congratulations. You successfully used Git, and this is how the Git's going to be used for most part. Except that what you've done so far is a history tracking on your machine. Meaning that if your laptop explodes out at this moment, all your changes are gone. Despite the fact you've been tracking it. It doesn't really matter. Everything lives on your computer. If your computer is gone, everything's gone. So, this is to say that you actually want to make a copy somewhere. You want a backup, right? Well, that's where GitHub comes into play. So say hello to GitHub. GitHub is a basically online Git repository hosting service. And basically what you can do is you can make a copy of your Git repository, which again is not a fancy way of saying a project or folder managed under Git, and just make a copy of it and keep it on this service called GitHub. It's just kind of like a Dropbox, but it's a much fancier way because it understands this is Git and gives you a lot more features on top. And there are terminologies that we'll actually visit. You can push and pull to and from GitHub to reflect changes you made or changes made elsewhere and synchronize it locally. And this also lets you do collaboration in the means of making clones. So anyways, the bottom line is this is like a perfect way and the standard way for people to make backup of your Git repository. So even if you're not going to work with anyone else, you're just going to completely keep everything to yourself because you really just want to don't share anything with anyone else, fine, I respect that decision. At least still use GitHub because it lets you make a backup. If you want to work with anyone else, this is also a perfect way by which you can tell people to go to a certain place, get access to your code, and start working on it together. Okay, so here's some schematic on how GitHub's going to work. So basically, as you make more and more commits, notice these are different commits. I'm actually used features that I haven't quite described to you called branchings and stuff. I'm not going to really cover everything and everything about Git. There's just simply no space for that in this course. But now, hopefully, you're initiated. You can read some of those Git tutorials, and things make much more sense. But basically, you can make branches in the commits to try something out temporarily and put it back. All in all, your Git commits can actually pile up and start to look a bit complicated. Here, basically, you have a lot of commits made, and blue one is just happening to point to the latest, the most recent commit, just to indicate what this is. This is called the tip of your Git commits. Okay? The way it works, basically, on GitHub, you create an empty repository to be your target, and you point your local repository to the target. And after you do that, what you can do, git push to synchronize everything you have from local repository onto GitHub. So that's where you have a perfect copy of your Git repository. And say you make additional commit. You're working on something, you made a new commit. When you change, shown red here, you just push it again, and now it gets there. New commit is also on GitHub. So GitHub is a perfect way to track changes and just have a place where it's a backup of your code. Okay. And then now keep in mind that let me just one point to keep in mind is that all the commits are basically history of changes you made, right? So because I'm copying the whole thing and not just the latest commit, this means that in both on your local machine as well as on GitHub, the entire history of your project exists. So this is a reason by which the Git is called a distributed version control system. Everyone who has a copy has entire history. There's no one place that has the entire history where you're only checking out a version from. Okay? This means that if you happen to have a whole repository copy on your local machine and GitHub and then another machine, in the extremely unlikely event that GitHub explodes and you lost GitHub track, you still have the entire history in front of you as well as on your other copy. Okay? So this is a very nice way to make sure that your entire history is always backed up together. Okay, so let's actually go ahead and do GitHub portions of this. So this is the point where you get to go to github.com. So open up a browser, go to GitHub. Using Jupyter Hub, I know you have a GitHub account. So go ahead, log into your GitHub. And I'll give you some time. Once you're there, what we're going to do is we're going to create a new repository by hitting plus, or you can actually do new repository here. But let's hit plus. Hopefully it's on the top right. Click new repository, and it gets you some options. So it basically says, okay, it's going to be created under your user account. If you happen to belong to another organization, you get to choose it. For most likely, you only have yourself as a choice. Repository name, this is the name of the repository. You can give it whatever name you like. Since we were working on this project, what do you call it, Python project or something? I'm just going to keep it the same name. I'm going to call it Python project. I bet, yeah. And give some description. So here I'm going to say like a demo project for GitHub for workshop in 2018. Keep it public. So public means that once you make this repository, everyone in the world can see it. Okay? If you have an educational account, or if you're actually willing to pay GitHub, you can actually make free private repositories. I think even if you don't pay, you get few private repositories for free anyway. But since you are all belonging to institution, I bet then you can actually use your EDU license to go through the process of educational account creation. And once you do that, or just change your account to educational account, once you do that, then you actually get free private repositories. But since there's nothing to be shameful or nothing to hide in this very fancy project we just created, we're just going to keep it public. And this here we're not going to do, we are just going to push what we already have in here. So we're not going to try to put anything in it. So don't initialize the repository with the README. So keep this unchecked and just create the repository. Okay, this takes a couple of seconds. And now it has created a repository. It's completely empty. Okay. Now what we get to do is go to your terminal. And what we're going to do is point our local repository to this GitHub repository. And in fact, if you read this, it actually tells you how to do that. You see there's a command right there. You can actually go ahead and copy and paste it if you like. I was going to copy and type in exactly the same thing anyway. So you can go ahead and copy those 2 lines and paste it in. Or if you want some practice typing, you can go ahead and type it up. So it depends on your setup. It will ask for username and password in the Git. Yeah, since you're pushing, yeah. So that's the username and password for your GitHub account. Okay.
That doesn't have to be the same one you initialized Git globally with.
No. It's whatever you use in the GitHub. Yeah. So yeah, you need to be able to recover your username and password for GitHub because unfortunately I don't know it. Okay, so for those of you who already successfully pushed, now if you go back to the project repository on GitHub and if you refresh it, hopefully you see your grandiose file you created. Hello.py should be there. And you can even click on it to see what's inside. In my case, I have very fancy 3 lines of code in there. So if you're here, you have successfully pushed your local repository onto GitHub. So by show of hands, who has the working version? Does it work? Yeah? Who's still having trouble? Okay, that I cannot help, yeah.
So what happens if you're doing this with Jupyter Lab and it's kind of modular code, it's not a script? Does that show up in there like a script, I guess?
Well, so it's going to show up in terms of either notebook or you'll actually see in a few seconds because what next thing I'm going to make you guys do is fork the repository for the whole workshop. Okay. All right. So hopefully you'll be able to catch up with this, and then I'm just going to start to proceed. Okay. So what you've done is at least make pushes. So what I want to do now is just go ahead for us to make one more commit. So just make whatever changes you like. Here I'm going to do explanation, something like I'm going to put one more. Go back here, probably make another comment, say a series of messages will be printed. Maybe I'm just going to change it instead of adding. And again, I'm going to go here. Fine, I'm just going to use this interface. Change looks good. Add it. I'm going to say update message. I'm committing it. So far, so good. This time, I'm going to show you how to push from within the VS Code. You can, okay? I can actually show both ways, yeah?
Somehow mine becomes a read only.
Read,
check.
So you have to go. This is because it's in showing changes. You have to go to the file itself to look at the change. Yeah. If you're looking at it, I actually made the same exact mistake up here now. I just pretended like nothing happened. So if you click on this ... section of your VS Code Git side of things, hopefully you see that there is push. What this means is that, well, you get to push to the GitHub online. Okay, so this is one way by which you can achieve push. So once you make the commit, you can push the new commits to the GitHub, and because this is all set up already, right? Because we already did the git remote add and all those things that GitHub initially suggested for you to do. You can go ahead and push it. So if I push it, it pushes the change. It's taking some time, and if you just go back to GitHub and check it, you should be able to see the new change was made. Okay? So this is via VS Code if you want to push stuff.
But we always have to go through those line of code in the terminal before pushing, right? So we have to add, commit, and then push.
So you have to add and commit and then push. That's absolutely true. But you could do add and commit all within VS Code as well.
Okay.
Yeah.
What about that message?
Let's say, would you like code to periodically run git fetch? If this shows up, this is basically saying, if it's the case that someone else, which could be you, make changes to GitHub, and you want to be aware of the fact that there are new commits on GitHub that is not local here, do you want the VS Code to check and let you know of that periodically? Answer is most likely yes. So you can say yes. And it's a bit hard for me to demonstrate git pull on this because it's really hard for me to show you making changes elsewhere situation right now because you're all making changes locally. But if you were to say go to another computer, take the repository, and then make changes and push it to the same GitHub, you can actually pull the changes onto your other machine just by running git pull. Okay, we'll see scenarios of that in the next project, which is coming up right now, where we're actually going to all work together on one repository. Okay, yeah, or at least pull is going to come up next session because the first thing I'm going to make you do next session is pull changes. Okay, with that being said, let's go ahead and do the next portion. So are we all good? Yeah. All right. So next session again, back to the presentation. So you've seen how GitHub works. The next big question, however, is like, what if you want to collaborate with others, like other people, multiple people working on same repository? Well, so there's a collaborative workflow in GitHub, and I'm going to describe this now. So basically, say me and Chris, who's not here, I'm just actually referring to a real person. Chris wants to work on one project called it's under some project folder, some places in GitHub, MyLab pipeline. So it could just be very well like under your name of the project. We're going to talk about a case where there's an organization and there's a repository underneath. That's a good way to share things. So we both want to work on this. So the very first thing to do is, and you get to do this shortly, is you'd fork the repository on GitHub. And what this does is it creates a complete copy of it under your user account. So now my user account is EY Walker, so I make a copy of the pipeline repository under my namespace or my user account on GitHub. That's called forking. So I forked the original repository, and so did Chris. His username is Ixicat, so he actually has this under his user account. Now this still lives all on GitHub. Now I can clone this repository, and we'll work on this. We'll clone the repository to bring it to our local machine. So this way, now this last copy is on my laptop. Okay, so now everything is in sync because I started with the original, I forked it, and then I cloned it. Everything is in sync with what's called the upstream, the very top source. Now say Chris is working very eagerly on this, so he made a new commit. What he gets to do first is he pushes it to his copy in his user account, just like how we pushed our commit to the GitHub. Notice that this red commit, the new commit, only exists in his local machine and now on his GitHub account. but not at the upstream nor in any of my things. What he gets to do now is he makes a pull request on GitHub, which basically prompts whoever that belongs to the same organization that, okay, there's some changes he made that he wants to share with the rest. He doesn't actually just get to push it. He actually makes a pull request, which prompts people like me to review the code. And if I'm happy with it, then I accept the pull request, which puts it into the upstream. Okay? So now it's an upstream. Now I'm the only one who's not synced. What I get to do now is on my laptop, I pull the change from upstream. So my laptop is in sync. And then finally, I push it to my user account. And finally, everything is back in sync. So this a bit roundabout dancing of pushing and pulling and forking and upstream, pull requests is a very standard routine by which people achieve sharing of code with the added benefit of checking changes. So the fact that when a person makes a pull request, people like me or whoever's working together gets a chance to check and approve or disapprove a change. So when you actually disapprove, you don't just say, I don't like it. You're supposed to say, what is it the problem you have with it? Suggest changes to be made. And another person gets to work on it, make additional commit. You get to see what are the new changes. And once you're finally happy with it, you accept the pull request. So this becomes a very standard and nicely established collaborative workflow when working around GitHub. This is the strength of GitHub. This is the reason for which GitHub has become very popular, is because this lets you share code, and not only share code, but make it easy for a lot of people to contribute to the code, but without creating a complete mess. Just imagine like you shared code for people to work on it, and one person thought, okay, this would be a nice change, and just make a change without letting you know. It may work in one regard, but it might have broken other things. If you have to constantly chase after changes that other people made and you're not notified of the changes, it becomes a complete mess to maintain a working repository. This system allows you to have more of a separated step where there's always a working copy, the upstream, and any changes made to it occurs via checks, via pull requests. So only when you're sure this is a good change and you've tested it through, you accept the pull request, put it into upstream, and you maintain that upstream is always a working code. Okay, so yeah, good practice. So this actually kind of comes to say that good practice around code management, code repository sharing, and checking, and all these things are essential when it comes to sharing code. It's not so much just about the tool, but it's about the policy of how to use your tool. So pull request workflow is by far the most popular workflow in the open source sharing community. So when they actually contribute to anything about open source coding, very likely they have a Git repository, a GitHub repository that you can fork, clone, and then clone, work on it. And once you're happy with the changes you made, you can make a pull request suggesting to the authors that, hey, I made some changes, I think it's useful, could you accept? And they're usually very good, and they have established workflow around when they check, how they're going to check, and maybe they'll suggest changes, or if they're happy, they'll accept, and you have successfully contributed to an open source endeavor. So after this, outside of the context of this course, if this sounds interesting to you, I highly encourage you to just go look up on GitHub, look at some project that might seem relevant, maybe pick one that's not the most popular because it tends to be easier ones to contribute to. Super cutting edge popular one tends to have a lot of people working on it, and it's a beast. But there are definitely many, many projects out there that you can just look at people's code, and maybe have a thing or two to contribute about. All right. Right. So yeah, one key thing I wanted to say is that in the midst of all these tools and policies, nothing ever replaces good communication. So I tend to give this particular part of the lecture in many contexts as a workshop towards a group of scientists, research groups, on how to share code, how to manage. I do give those kind of workshops going around different institutions. And you'd be shocked that this is not sometimes kind of ignored. Right? They kind of assume that tools will help. It will help, but that will never replace communication. So I always have the line in there. It's like you guys should always be talking to each other. Okay, well, with that enough said about it, let's actually try this forking methodology. Go back to GitHub, and this time I want you to go. I'm actually just going to give you a link to it to make it easier. So just give me a second. So I'm posting this link on the channel, so you can just click on it. So if you go there, you should be able to see a repository for what should look somewhat familiar. Yeah? This should look familiar. Please say yes, right? This is the collection of notebooks you've been working on with the Jupyter Hub. Yes, all the way through you actually were silently using Git because I manage everything using Git and GitHub. So this is the project repository, and I do plan to keep this always updated. And after the course is done, I'll keep it like this. So basically, you always can go back. You can point other people to this repository to look at the code. They can actually try the notebooks. That's how this is going to be maintained. Anyway, so what I want you to do now is for you guys to fork this and clone. So let's go through that process. To fork, if you at least survey the interface enough, you should see there's a fork right there. Yeah. So if you click on the fork, it will suggest, okay, if you want to fork, where do you want to fork it into? It will suggest either your user account or all the other organizations you belong to. I belong to about 20 other organizations, so my list is pretty long, but just pick your username. If you do that, it's going to start the forking procedure. So it's just making a copy of the whole repository under your user account. Okay? And I expect you all to do that. I can sort of tell if you guys are doing it by counting up how many forks exist. So hopefully you've forked it, and now you have your own copy of this under your user account. So you should be able to verify by looking at the fact that it should say your username / Python Neuro 2018. Okay. So far so good? Everything's working? Yes? Okay. Now what we get to do is we get to clone this repository on your own laptop. So go to the terminal we all have come to love, or command prompt, yeah? And this time I want to clone it. So every time you clone, it takes the whole project and puts us a folder. So you have to start where you want to put that folder in. I'm currently still in my Python project folder, so I don't think I want to put this whole thing inside Python project. So I want to move one level up. So you can do that by cd ... to indicate go one folder up. Okay, you can verify the fact that you're now in Documents folder. Hopefully that's the case. Yeah, if you're not sure, just list or dir to see what's in there. Once you're okay with where the location is, you're okay to clone the repository, you get to do git clone and the address of the GitHub repository you want to clone. So if you're looking at the GitHub page, you can either just go ahead and copy this address, or if you look, if there's a green button say clone or download. If you go there, it actually also gives you an address that you can use. So you can use either or, it's the same thing usually. So you copy that, go to terminal, pasted it after git clone, and if you enter it, it starts the cloning procedure. It's not the biggest thing, but it's not the smallest thing, so it might take a couple of seconds for it to clone. Okay, so in my case, it's now done. If I list or dir where I am, it should have created a new folder. That's the name of the repository. So it's Python Neuro 2018. Once you're this far, move into Python Neuro 2018. And if you list or dir, you should be able to see all the notebooks and content of the repository so far. Okay, so far so good? All right.
Is it different to cd dot in Windows?
It should be the same.
I just keep it in the same folder because for some reason it says the command's not found.
CD with space?
Oh, maybe that's
Yeah, sorry. So cd space ... yeah. Yeah. So let's go ahead and actually open up VS Code. The VS Code is currently still pointing to your other project, the Python project. So what we want is another instance of VS Code now pointing at the repository we just cloned. You can either just quit out of this current one and then just do open workspace. And this time choose Python Neuro 2018. Does it actually not let me do that? Oh, so it's not the workspace. I have to say open. Sorry, not the open workspace. Open in Python Neuro 2018. It will take some time to open it up, but it should be able to show everything. Yeah. Now, just one thing to point out. If you look at any of the IPython notebook inside VS Code, it looks like a mess. of text, it doesn't show up in one of those nicely formatted notebooks. This is actually what an IPython notebook looks in terms of data. If you look at the text file that represents the notebook, this is actually what the content is. Please don't try to edit it because editing outside of notebook really usually creates a complete mess. I'm just pointing out the IPython notebook, unless you're looking through a particular browser or particular viewer, wouldn't look anything like a good fancy notebook that you're used to now. Okay, so far so good. Everyone got this far? You have a repository successfully opened with VS Code. So what I want you to do now is actually open this as a notebook. So again, back in terminal, still in the folder Python Neuro 2018, run the command Jupyter Lab, which if you really follow the instructions, you should be working on your setup. Run it. And now you should be back to what should look really familiar. Very similar interface to what you've had from my Jupyter Hub from last week. But now everything is actually running on your machine. So from today onward, this is the interface we're going to all work with. Okay? You get to actually run notebooks on your computer and make changes there. Okay? There's one last piece that I have to cover now, which is how to get updates. So here you hopefully see there's a notebook for 03, which is the third session on the NumPy. So that's already there. But between now and next session, I'm going to create another notebook for next session, which is going to be 04, something along the line of NumPy and Matplotlib, which is going to only exist in the upstream repository. Okay, so that's going to be a situation very similar to where the change exists upstream. So I'll push the change here. But on your copy on your GitHub user account or your local wouldn't have the change unless you pull it. So you get to actually learn how to do pulling. And we're going to actually really practice it next time because so far I don't have a change to really show. Actually, I can do a demo. But at least before you can actually do that, you have to set your local repository to learn to point to the upstream as an upstream. Because at the moment, only thing it's aware of is the fact that this is what's called origin. You clone this repository, so your local repository in your laptop knows something about your account's GitHub the copy, but it doesn't know anything about where this was forked from. It doesn't actually have a way to automatically do that. So you have to tell them that this is an upstream that you can actually point to. So let's actually go ahead and do that procedure right now. So if you open up a terminal, it should still kind of look like this because it's still running your Jupyter Lab. So there are a couple of ways to quit it. You can either just close out the terminal and open up a new terminal, or before you do that, or probably easier, because if you did that, you have to do a CD to navigate back to the same location. If you say, and actually if you read it somewhere, it should say, use Control-C to stop this server and shut down. So you can actually just do that. So hit Control-C twice. Okay, and it should stop the notebook. And it should be, if you go back to the browser that had the Jupyter Lab, it should now say server connection error because you killed the server. Okay, so this is all to also indicate that everything's actually running on your laptop. Just because you're accessing via browser doesn't mean there's somewhere a magical website that was created for you elsewhere. It's all running on your laptop. Okay, but now we stop this, so we actually are back to terminal being in the repository. What we have to do is tell Git that we want to point to the upstream and call that pointer, well, upstream. So the way you do that is you say git remote add upstream, and you have to give address of the upstream. The address of the upstream is not your GitHub repository, but the original. So if you kind of go back, it should be basically Edgar's guide / Python Neuro 2018. You can either just take that address from the address bar, or if you go to clone, download button, it will also give you there. So it should be the same thing. Just copy the address, and then paste it right after git remote add upstream, the address. Okay? And now you have successfully added the remote. Okay, so yeah, it worked.
So you have to be in the folder.
You have to be in the folder. You have to be in the Git folder of that repository. So far, so good. Now you can list all the remote repository that your local repository is associated by saying git remote. And to give a bit more description, do -v. for verbose, meaning it gives a bit more than just names. And it has two things per, but most important thing is just basically there are origin and upstream. Origin is the pointing to your account because you cloned from it. It automatically creates this connection. But upstream is the one you just created. And you use this origin or upstream when you push or pull by specifying the name. So far we've actually been doing pushes when you make changes, right? But we can actually do a quick test with the pull. So actually for me to do that, let me just quickly, so this part is just going to be me, so just hold on a second. I'm going to basically go and create a quick change. Okay, I'm going to say test.py. All right. So what I have just done is I added some changes to the original. So if you go back to the GitHub and look at Edgar's guide, Python and Neuron 2018, and if you look at it now, I've created this quite useless test.py file, right? And if you look at your fork, this should not be there. So in fact, I do recommend you try to go to your fork. Okay. Test.py should not be there. And not only that, if you look carefully, this should say this branch is one commit behind towards the top right there. So this indicates that your fork is now behind. Like there are changes upstream that's been made that you still don't have reflected in your copy here. Okay? Make sense so far? So now go to the terminal and make sure you're inside your copy. If you now do git status, maybe it should still, maybe it probably still wouldn't say anything about like changes made upstream. What you can do now is you can say git pull upstream to get the changes from the upstream to your local copy. If you run it, it should work without any problem. You ask to pull from remote. Why is it not working for me? The default did not specify. Oh, sorry. You have to say git pull upstream master. My bad. You have to say master because technically we're working with a branch called master branch. Because we haven't created any other branches, the only branch that exists is master. As I said, I'm not going to really have time to cover this particular topic of branching in Git, at least not in the context of this course. If there's enough demand, I'll be happy to cover it since I covered this thing in the past outside of the context of the course, or I could just point you to a couple of resources towards that. Anyway, once you run git pull upstream master, hopefully it should say something like updating it, there's a fast forward change, and you should see now there's a test.py locally. Okay? You're not done yet. What you've done is basically, in terms of our presentation, you've pulled, so your local copy now has to change from the upstream, but your fork on GitHub still doesn't have this. So the last bit that's missing is for you to push this to your account's version. So you can just do that. It's like git push. If you say git push, by default, it will point to origin master. Okay, but you could be very specific, and you could say origin master to be, extra sure. But usually you don't have to do this. You can just say git push. It will know to push to where you cloned from, which is your fork. I know I'm using a lot of new terminologies, so hopefully this is still somewhat coming in. But this is not the last time you get to do this. So for the rest of the courses, sessions, you actually hope you get more and more practice with doing this routine. Okay, any questions thus far? This is all sort of makes sense. So basically, from now on, at the beginning of every session, I'm gonna ask you to pull from the upstream to get the latest of the changes. So this time I made you, get the test.py, which is quite useless. But in the future, it'll be more useful changes like new notebooks for that particular session. So you do want to start your day in the course with git pull upstream or upstream master to get the latest notebooks, so you can we can all work on the same thing. Okay, and make sure you also push it to your fork, just so that you have all the changes. One thing I want you to do between today and next session is to go to the Jupyter Hub. All right, so if you're actually going to show, if you go back to the Jupyter Hub, I believe you made a bunch of changes to your notebook, right? So what you should do is and I mean, unless you don't care about all the changes and all the things you tried, at least for the stuff like homework assignments, you should try to download. So this actually here exactly corresponds to what was the content of the repository. So what you could do is just download any of the notebooks, put it in the folder, add it, commit it, and push to your account. So this way, your GitHub repository will contain all the changes in the notebook you want and you made. Okay? If you don't care about it, you don't have to do it, but it's a good practice to do commits, add and commits, and then pushes. Yes, what's up?
So then if we pull from your master
Would it conflict?
upstream, yeah, what would happen?
Good question. So it wouldn't conflict because I will never make changes to the stuff I'm already giving you guys. Yeah, that's the only way to deal with this. Well, so that should be fine. Like basically, if you copy it over, it will be registered as you just made a whole bunch of changes to an existing file that you're committing. Yeah, yeah.
So it will say we're not up to date with Edgar.
It will say you're ahead because you have more commits than what I have. Yeah, which is usually fine. Okay. If that ever arises, if the conflict occurs, then I'll deal with it case by case. I'm grossing over this one very favorite topic of Git and GitHub users called merge conflicts or conflicts. Basically, that is like what happens if two people make changes to the same file and they both make commits, and now you're trying to merge them together. How do you deal with it? It's actually not the easiest topic because it actually is really usually case by case on how to deal with it. If you do enough routine of making sure you pull the latest changes and push as soon as you made some changes, it actually so turns that most of the time you don't run into this. So if you run into merge conflict all the time, most likely the problem is not so much about you two work and the multiple people working, it's like lack of communication. But if that ever arises, I'll cover that topic. Yes?
Just to make sure I understood. So if I make changes to my local copy,
That's right.
and I pull from upstream,
Yeah, that's right.
and that will not make my changes disappear.
It wouldn't make your changes disappear. Yeah. As long as the changes are about different files, Git will automatically merge the changes you made and change that was made elsewhere into the next commit. Okay. The problem occurs when changes were about the same file or even about the same line of code. If it's the same file but different lines of code, Git is usually pretty good about merging them together. But if two people try to change the same line of code, obviously you have to do something about that. And Git wouldn't make that decision for you. Git will actually ask you to come up with a solution. Okay, so that's all I wanted to cover with Git. Any questions so far? Has everything worked out? I know this was going to be a pretty lengthy process, but I did want to cover it. I know this is not per se part of Python or neuroanalysis, but I do strongly believe that nowadays, if anyone gets taught how to do a coding, you need to know Git, right? And this is in many regards. Like if you're gonna ever work in like a project that involves multiple people, source control or version control like this is essential. If you don't have one like this, you will have an issue with your project. I can guarantee you that. And also when it comes to just looking for a job market, and I can just quickly touch on that too. If you're like say gonna work on as a data scientist from here on, or if you're interested in industry jobs that involves any sort of coding, Git and GitHub is considered like absolute essential. They will all require you to pretty much know what this is. So that's the expectation. Okay, so just thought we should cover that. All right, so with that said, let's go ahead and actually go into the topic that was part of the syllabus, which is NumPy. And I'm just switching gears now. So you should be in that thing you cloned, right? The Python Neuron 2018. Start Jupyter Lab again. And then open up the notebook tree. As usual, this has is a pretty lengthy notebook, so it takes a couple seconds to load. I don't know if I'm going to ever get to the point where notebooks are shorter. I'm thinking about maybe breaking it up, but I think a couple seconds is fine. All right. So in the next 25 minutes or so, we'll start with NumPy, and we'll finish it off next time along with matplotlib, which is a plotting package. Okay. And just to lay out some expectations, so one thing I forgot to mention at the very beginning is that yes, today was the homework assignment due date, right? I know you're not graded. You know you're not graded as well. So yeah, you don't have any penalty for not submitting a homework, but it's considered more as an opportunity to get your code reviewed. All right. So if you have submitted it, what I'm gonna do is I'm gonna go through the submitted homework assignments, and I'm gonna go through, make some comments, make some suggestions, and once I'm done with it, I'm gonna change the trailing name of the homework assignment you submitted with saying graded. So if your thing has graded underscore graded at the end, that means I'm done reviewing it. So you should take a look at it. I might even announce it on the Slack channel, and just consider it as an input coming from someone who has a lot of experience with coding in terms of what you could have improved, what things would have been smoother, maybe some additional comments you're supposed to provide. So it's just a good practice to get used to being critiqued on your code, and it just in general helps you with your coding style. Another thing I do highly recommend is actually take a look at other people's submission. Right? So in the public folder, you can see everyone else's submission. So you can actually go ahead, take a look at others' code and see if it makes sense. See if they approach the same way, or maybe they approach in completely different ways. When it comes to coding, there's hardly ever the right answer. There's always multiple ways of approaching the same problem. And trying to read someone else's code and understanding how they approach it is a very good practice for you to actually increase your understanding of how to program. So those are the main points. The homework from now on will be weekly assignments. It just, quite honestly, out of my lack of my own time, I can't quite do every session assignment. And also on top of it, I think just too much to begin with. So I'm going to assign homeworks on the second session of the week. So I'll be assigning a homework on Thursday, expecting you to finish it by the first session of the following week. Okay. Submission format is going to be a bit different. You can probably kind of guess that I'm going to actually ask you to create a repository and tell me your repository, which I'm going to review. And my grading is going to come in the form of pull requests. They say, I'm going to suggest how to change your code, and you get to kind of look at it. At least that's one way I'm thinking about how to do this. Okay, so far so good? Make sense? All right, so with that, let's actually dive into NumPy. So, when you start working on numerical computation, this is where you actually start to be more specific usage of Python. Python itself is a very generic programming language. You can really start to use it to whatever purposes you like. You can build a website, you can build a phone application, or you can just build something that plays and talks to you if that's what you want to do. But for our purposes, we are interested in using Python for the purpose of scientific computations, for helping us do research. So in that context, you're obviously interested in using this as some sort of fancy way to do numerical computations. And when you work with those, you very quickly encounter needs to do something like vectors, matrices, or even higher dimensional structures like tensors. Well, you could imagine vector is sort of like a list, right? So I could create vector 1, 1, 2, 3, vector 2, 4, 5, 6. Okay, I mean, that looks fine. Now I want to do vector addition. So if you remember vector addition, it adds element by element corresponding in position. So, okay, can I just do v1 plus v2? Well, you guys should know that if I did that, it concatenates a list. So addition of two lists doesn't quite correspond to vector addition, right? So this doesn't really achieve what you're looking for. Okay, you can write a function that actually achieves vector addition. So here I've written a function. I'm not going to really go through the details. It just basically steps each position, creates a new list, which is sum element-wise. So I can use that, and now I can achieve vector addition. Fine, but it's kind of annoying if I have to define this every single time. I mean, especially what if I want to do dot products? What if I want to do cross products? What if it's matrices addition? It becomes harder and harder if I have to stick with list, or even list of lists, or list of list of lists if you're trying to go for more higher order structures. Okay, so you probably can guess, and you can even already skip ahead and read. Yes, the solution is to use a package provided specifically for this purpose called NumPy. NumPy is a Python package. So what is a package as opposed to module? Module is more like one file with a bunch of Python functions and code that you can import. Package is a collection of multiple such modules. So you can just imagine it's a big project with a lot of code. So you can import a NumPy package, and one of the key things it provides is a numerical array, which is sort of like a vector, matrices, or tensors that has the capacities in terms of vector and matrix additions and multiplication that you would expect out of any good numerical computation package. Okay, so let's import it. You import a package just like you import a module, just by saying import the name of the package. And the convention is to rename it as well. So you can just import NumPy and just start using NumPy dot to keep on using its content. Just typing that 5 characters seems ridiculously long, so you abbreviate it by importing as an alias NP, which is the convention for using NumPy. Okay? So let's learn how to create an array. With NumPy, you can turn a list into an array by simply having np.array, which is a function that takes in a list, and it returns a NumPy array object. So I created an array. If you look at it, it says it's an array of content 1, 2, 3, based on the list. Okay, you can create another one, B, which is NumPy array of 4, 5, and 6. And now this time, let's go ahead and try the sum of 2 vectors again. Notice we're not adding 2 lists. We're adding 2 NumPy arrays. If you add them, you actually get the vector addition you expect. You can also get dot product by using this special @ symbol. Okay, and if you're curious, you can verify this is a dot product. So very typically, you create an array of 1 dimension. So this is equivalent almost to a vector, but more commonly referred to as 1D array in NumPy. And you can check a couple properties of the NumPy array object you created by looking at the properties. So remember the object-oriented discussion we had. An object, because of the class definition, will have properties and methods. Same thing goes with NumPy objects. They're just an object, so we have a couple properties you can look at and a couple methods you can use. So ndim is a property which stands for number of dimensions. So since this is a 1D array, just a flat array, dimension is 1. And shape gives you the shape of an array as a tuple. In this case, this is a 5-element array, so this would be a tuple with just 5 inside. Okay? You can create a 2D array by passing a list of lists. You have to just make sure that individual lists are of the same length, just to represent the matrix. So here I'm having a 2x3 matrix represented by passing 0, 1, 2, which corresponds to the first row of the matrix, and 3, 4, 5 for the second row of the matrix. You create the array, and you get a 2x3 matrix, or 2D array, which has ndim of 2 and shape of 2, 3 for 2x3 matrix. So far, so good? Okay, so far we actually look at creating arrays by passing in list or list of lists where you specify every element yourself. Once in a while you do have to do this, but for 99% of the time you don't create an array like that. That's just way too much work. You use one of the utility functions provided by NumPy to create a very standard starting point arrays which you can use it as is or modify to be the exact array you're interested in. So remember the range function that we used when we were talking about iteration? So range represents a range of numbers, right? So if I say range 10, that represents an iterable object that goes from 0 all the way up to, but not including 10, so stops at 9. So remember that? There's a similar function in NumPy called np.arange, A for array. And what it does is basically gives you the range, but as a NumPy array. So if you do np.arange10, it gives you a sequence of number going from 0 all the way up to 10, but not including 10. So an array, 1D array from 0 to 9. And just like range, you can actually specify start and stop. So I can start at 5 and end at, but not include 10. So that's 5, 6, 7, 8, 9. And again, just like range, you can provide a step. So you can do every other element. So in this case, if I go from 3 to 30 with step of 2, it's 3, 5, 7 onward up to, but not including 30, which would have not been included anyway. Okay, so this is one way by which you can get a sequence of numbers as an array very quickly. Now, alternatively, what you might want to do is you want to know, you know that you want to start somewhere and end somewhere and just equally fill the space in between with some pre-specified number of data points. This happens a lot, especially when we start looking at plotting. So here, let's just say I'm interested in having a range that goes from 0 to 1 with 5 points equally spaced apart, including the ending of 0 and 1. You do that by using this function under NumPy called linspace for linear space. And if you do 0, 1, 5, it gives you 0 to 1 with total 5 points equally spaced apart. In this case, spaced apart by 0.25. You can, of course, go overboard. You can go from 0 to 1 with 100 points total. It gives you equally spaced 100 points. Now, another very common thing you want to do is create an array of specific size and dimensions, or shapes and dimensions, that is pre-filled with single value, maybe 0, maybe 1. You can use that, but you can do that by using the zeros function or ones function. Zeros expect you to pass in a tuple that specifies a shape. So that's a bit tricky. Unless you only have one dimension, then you can actually just give that one number, it understands it. But if you want to create, say, a 3 by 3 array, so 3 by 3 two-dimensional NumPy array that's filled with zeros, you do np zeros and pass in 3, 3 as a tuple. And you get this. If you want it filled with ones instead, you can obviously just do ones and pass in the shape. So here I'm creating 3 by 4 2D array filled with ones. Once in a while, you actually want your NumPy array to be randomly initialized. So have a bunch of numbers in that is not all 0, not all 1, but some random numbers. Now, when you talk about random, there are obviously many kinds of randomness. And I'm not going to quite go into the topic because that's a whole other discussion, but it's a very fun topic. So maybe one day I get to teach a course on it. But it's about sampling. It's about sampling from a distribution. So at least NumPy, at least straightforwardly comes with two that you can already start to use. One is a uniform distribution. So if you do random, just rand, so if you say np.random.ran, and here you specify shape, I know here you have to specify shape not in a tuple, but you just list out the numbers. It's an inconsistency in NumPy, so it's a bit annoying, but that's just how it is. And this samples from each position, randomly samples from a uniform distribution between 0 and 1. So if you look at it, that's what it gives. So none of the numbers should be less than 0. None of them would be greater than 1. And if you just run it a couple of times, every time you run it, it will give you different results because it's just always randomly sampling. Another very common thing you want to sample from is, of course, Gaussian or normal distributions. It will sample from a standard normal, meaning it has a mean of 0 and standard deviation of 1. It doesn't quite make any sense to you, don't worry about it, but it's pretty typical, it's pretty standard and pretty useful thing to sample from. So here if you sample from, you will see some negative numbers. In fact, good 50% of them should be about negative. But every time you run, again, you get different samples from the normal distribution. Just to throw out some jargon, this is independent sample from identically distributed, or IID samples from normal distribution. Again, if that makes sense to you, great. If not, don't worry about it. Okay, there are other special matrices that you once in a while would like to create. One, for example, is identity matrix. And for those of you who are not quite familiar with identity matrix, it's just a matrix where diagonals are ones and everything else is 0. So I can create, say, a 4 by 4 identity matrix by using MPI function, and they just, a cute thing, they decided to call it I. Yeah, I know. They put, if you pass in the dimension, if you pass 4, by default creates 4 by 4 identity matrix. So only the diagonals are 1, everything else is 0. Or if you actually want to create a diagonal matrix where diagonal entries are what you specified and everything else is 0, you use the diag function or diag function passing a list of numbers to serve as a diagonal entries. Here I'm passing in 1, 2, 3, 4, so that should be my diagonal entry, creating a matrix that looks like this. Okay? Once in a while this comes up, probably don't use it all the time, but when you need it, pretty nice. Okay, one thing I do want to cover right now at the moment, although I'm going to revisit this topic of reshaping array, is to reshape an array. So for example, if you start with the A range, it gives you a 1D array that's flat, right? Well, what if I want a matrix, like 3 by 5 matrix, that's filled with sequences of numbers? Well, pretty much go from 0 to 14. What I can do is take the one I just created, which is a flat array, and kind of fold it into 3 by 5 matrix, giving it like this. You can use a reshape method on the array to change the shape of an array. Okay, so pay a bit special attention to how it folded it up. It folds it what's known as row-wise or last element first, last dimension first folding. Meaning that instead of going like column-wise 0, 1, 2, 3, 4, 5, it goes row-wise 0, 1, 2, 3, 4, and then on to the next row 5, 6, 7, 8, 9, so on and so forth. This is a particular choice. Obviously, they had to choose one, so they went with this last dimension first folding or row-wise folding. If you happen to be coming from other languages, for example, Fortran, or if you're coming from MATLAB more specifically, MATLAB reshaping is opposite. They are column-wise folding. So if you're to take a flat vector from 0 to 14 and fold it into 3 by 5, it will fill columns first. So be aware. Many things are very similar between MATLAB and NumPy, partially because NumPy was definitely inspired by MATLAB and how it handled, but decided to be different in many aspects. And this is one aspect that can quite screw you up if you don't pay careful attention to this. Okay, so for those of you who are already familiar with MATLAB, this is one thing to be aware of. If not, you should consider yourself very fortunate that you're only touching Python and don't worry about MATLAB, okay? Maybe I shouldn't have recorded that. Indexing and slicing arrays. So just like lists, you can index into an array and slice an array to create another array. So here I'm just creating one array. Let's go from 0 to 10, not including 10, so 0, 1, 2, 3, all the way up to 9. If I do a bracket 0, that's the first element, so I expect 0. Minus 1 is the last from the last element, so going backward from the ending. That should give me 9. 3 to 8 slices from index 3 up to, but not including index A. So here it will be 3, 4, 5, 6, 7. And do you guys remember? Actually, I told the answer. Well, I was about to ask, do you guys remember what this does? And obviously, I already gave an answer away. So if you do this, remember that when you slice, you can not only specify start and end by a step. And if you have a step that's negative, it visits from the end backward. So a very cheap way to reverse an array, especially if it's a flat array, is to do this colon, colon, -1 to say just reverse index. And this can reverse the array. Now, when it comes to multi-dimensional array, the indexing becomes a bit more interesting. So let's actually create a multi-index array by using the reshape trick we already just learned. So I'm going to create a 12 length vector and then fold it up into 3 by 4, which should look kind of like this. If I select 0, it indexes from the outer dimension to inner dimension. Outer dimensions are rows, and inner dimensions are columns in this case. So if I just say A0, it's the 0th row, or first row. If it's A-1, that's the last row. And if I do slicing, that's slicing on the row as well. So if I do column 2, it slices up to, but not including index 2 of the row, meaning the first 2 rows in this case. If you want to start indexing into the columns, what you do is you pass in the second number as part of your bracket notation. So if I say 0, 1, this picks the first row, second column, which is 1 number. So verify this corresponds to first row, second column. 2, 2 is row Yeah, row, no, it's index 2 for the row and index 2 for the column, so it should be 10, right? And you can also slice, and you can slice either of the dimensions the way you want. So this starts to get complicated, so just pay attention to it. The first number 1 means pick the row index 1. So you're looking at the second row. But the second one is a slice. So it slices up to 3. So this slices the first 3 columns out. So just go through this a couple times in your mind. If you run it, you get 4, 5, and 6. Okay, so let's just kind of go revisit this. This is a 1 and then slice column 3. So if you look, where's my array? There. So 1 selects the row index 1. And then from this array, I'm slicing out 0, 1, and 2, but not including index 3. So that should give you 4, 5, 6. Okay. This is something you just have to practice. You just do it multiple times, and eventually slicing becomes more and more intuitive and natural to you. So here's a way by which you can get the entire column. So getting a row was easy. You just use one number to index. If you want the entire column, you select every row with just giving a column. So column means slice out the entire row, but for the second column, or column index 2, sorry. So that's third column. That gives you 2, 6, and 10. Now notice that if I index it out, you give a 1D array back, right? We'll get back to this point more closely later, or in the perhaps next session. But just keep in mind, it just gives you those elements, usually as a flat 1D array. Okay? Now you can slice the multiple dimensions together. So here I'm recreating another 4x4 matrix. Now if I do 1 column 3, comma, 1 column 4, any guess what that would do? So first slicing is slicing off the rows, starting at index 1, and going up to, but not including index 3, so that should be second and third row. Next, slicing is on columns. So that should be starting at 1 and going up to, but not including index 4. Actually, I was wrong here. So up to, but not including 3. Actually, this wouldn't work. My bad. Actually, I meant to do this 1 column 3. Sorry, this should change it. And if I do this, this should select the middle 2x2 sub-matrices. Okay. These are the points that I want you between today and next session. Go over the notebook a couple of times. There's a couple of exercises to help you at the end to just see if you can solve it, to get familiar with this. The best way to get used to this is just keep on using it, see more and more examples, try out things, and that's how you get used to these things. All right, so let's cover at least modifying arrays. So far you already looked at how to create an array, a bit of reshaping, and you now can index and slice it. Armed with indexing and slicing, you can actually go in and start changing the content of an array. So just like list, NumPy array objects are mutable objects, meaning you can change them in place. So remember all the discussion about references to objects and how lists and dictionaries are mutable? Same thing applies to NumPy arrays. So here I'm creating a 3x5 matrix filled with zeros. And you can change one element at a time just by indexing up to one number and then assigning a value you want to assign it to. So here if I actually say 1, 2, so that should be 1, 2, yeah? And I assign 3 into it. If I look at it, I get 3 placed right in the middle. Now you can actually do even fancier thing. You can actually say change the entire row at once. You just select the row. Remember x0 will select the first row and assign 4 into it. And you get the first row entirely filled with 4s. You can even change this entire column using slicing index. Here I'm even fancy by saying -1 column, which is the last column. Okay. So with that, you get the last column now changed to 5. Now notice I overridden the 4 entry at the very end. So last change you apply always overrides whatever has been there, right? And even better, you can place an entire list in place of an existing row or column as long as the number of element matches. Okay, so either you put one number to fill the entire thing with that one number, or if you're going to replace it with the entire row, for example, you have to make sure the number of element matches. So here I want to replace the last row with a new array, new list actually, 10, 20, 30, 40, 50, and I'm just assigning into the last row. This should work. If I look at it, the last row is successfully replaced. Now, if I try to assign an array or list that's not matched up in size, it gives an error saying you cannot copy sequence with size 3 to array with dimension 5. So this should be a pretty obvious error. Like the dimension is not matching, or shape is not matching. So I think, let me just quickly look at it. Yeah, let's go and cover copies and views quickly, and then that's it for today. So let's create another one again. So 0 to 14, reshape into 3 by 5 matrix. And what I want to show is that when you actually take a slice out of it, so say one row out of it or one column out of an existing array, and now you change the array you extracted. So if you change the column you extracted, what happens to the original? So here I'm taking the second row out of it. I can look at the second row. So this is the second row from the original array right here. Now, if I look at the index 3, that's 8, right? Sorry, I should skipped it. No, that's correct. And now if I replace the number 8 with 100, and if I look at the row again, obviously that's changed. That's expected. Question is, what has happened to the original array where this row was extracted from? We notice it changed as well. So this is one tricky bit, useful but could be very tricky, is that if you do a slicing on array and get another array out of it, that's considered a view, meaning that it's still actually looking at same piece of memory. It's just a different way to look at it. So if you make changes using the view, it gets reflected on the original because they're actually always looking at the same part of the memory. So this is pretty nice, meaning that you get to extract a row and then within the row work on a particular column. But if you're just say passing around rows to some other function and the function decides to make a change, you can accidentally get a change in your original array, which might be an unexpected thing. So you have to just be aware of this property. If you want to avoid these accidental changes via views, instead of making a view, you want a copy of it. So you can make a copy by just taking, say in this case, I take x0, which is the first row. If I do it as is, this is a view. But if I do dot copy, it creates an entirely new copy of it, r. So now r is the first row's copy from the x. If I make changes to it, it would change r obviously, but it has nothing to do with the x. So you can see that x is intact this way. So just be aware every time you slice it, you're actually creating a view. And if you make changes to the view, the slice, it would change the original. Many times this is pretty useful. Sometimes you get caught by surprise. Okay, so I think that's where I'm going to finish off today. And we'll have a bit more to work through with NumPy. At the very end, I have prepared some NumPy exercises. Some you can already answer. Some you probably have to wait till I cover more topics, but you're more than welcome to attempt at it. I will provide answers by next time, so I'll have a completed version just like last time where it'd be a completed folder with the corresponding notebook that has all these things answered away. But do try it and do try just more than just this. You can also go Google for NumPy exercises and there are like hundreds, literally hundreds and thousands of exercises for you to try. I don't necessarily recommend you try all of them because there's really not a point in doing every single one of them. But try coming up with stuff. Like if you come up with a matrix, see if you can say get the center 3 by 3 matrix out of 10 by 4 matrix. Right? Trying things like that, the more exercise you've done, more natural this becomes to you, the easier NumPy gets to you. Okay? All right, that's all I have. Any questions? All right, so next time we'll continue with NumPy and we'll also visit plotting because we kind of want to get things visual. Right? We want to start looking at plotting, making things a bit more interactive and nice. And next week, just an overview. Next week, we actually try to visit actual neuroanalysis topics. So I'll cover some simple stuff that uses NumPy and Matplotlib in more realistic context when it comes to analyzing neuronal data, or maybe neuronal images. That being said, I'm actually pretty open to suggestions as to what you want to see covered. So maybe you're already working on some research topic that requires some sort of analysis. If you have some, something you want me to visit, you can shoot it to me. I'm not going to guarantee I'm going to go over it, but it might be a good one to try. So if you have some ideas, feel free to post it on Slack between now and the next week, and I'll make class content accordingly. Okay? Sounds good? All right, that's it.